Hello and welcome to Module 3, Lesson 2, Exponential Growth. I can write equations to represent exponential growth situations. That's what we're going to be working on today. So exponential growth, what is it? It's increasing an amount by a consistent percentage rate over time. It's a little different than what we've done in the first semester. Common types of exponential growth, places you'll see exponential growth are in population growth, compound interest, so like what banks do with your money, and inflation. So let's take a look back at what we talked about in first semester. With linear functions, you have f of x or y equals x, and you had a line. We had quadratic functions where we graphed them, where they made a u or parabola. We also did absolute value graphs, where the absolute value graph made a v. Now we're going to look at exponential functions. An exponential function is a function in the form y equals ab to the x. The big thing I want you to notice is where the variable x is located. It is an exponent, which is different. In all those previous ones on the previous slide, the x was the base. Okay, now we're talking about x as an exponent. Now, the a is the starting value. This will make more sense once we get to the first example. A cannot be 0. It also has to be positive. It has to be bigger than 0. The B value is probably the most confusing part. It's the growth factor. It's a percentage that we write as a decimal. B has to be greater than 1 with growth. Only with growth. Next lesson, we're going to talk about decay and what that's going to look like. And the easiest way for me to figure out the B value is do 100% plus whatever the rate as a percentage is. Again, this will make more sense when we do an example. X is going to be time, typically years, but it could be months, days, seconds, etc. So here's an example of what one would look like. So A in this case was 10,000. The B would be 1.25, and X is a variable. Okay? And that's what the graph is going to look like. It's not a line. It's not a U. It's kind of an upward curve with growth. Okay? I gave you this example before you did this lesson. I wanted you to think about this. Would you rather have $1 million or a penny a day doubled for 30 days? Okay, and if you did this math correctly, you came to probably a kind of a surprising conclusion. Okay, a lot of people are going to take the $1 million because why not? But look what happens if you do this as an exponential function. Y equals AB to the X. What's the starting amount? Well, it's a penny. A penny is 0.01. The B value, though, is a growth factor. You're doubling it. Doubling it means you're taking 100%, taking the original amount, and you're adding the original amount again. That's what doubling it means, which comes to 200%, which written as a decimal is just 2. X is time, and in this case, it's 30 days. So if you write an equation, you get y equals 0.01 times 2 to the 30th power. And if you do that, type that in your calculator, you'll get 10 million plus. You would have, if you did the penny doubled every day for 30 days, you would have over $10 million. Okay. Kind of surprising in how quickly this can grow. All right. More of what you're going to have to do. Okay. You deposit $3,600 in the bank. Determine how much money you will have in 20 years if your money earns 5% interest each year. So again, the equation is y equals AB to the X. We need A, B, and X. A is usually pretty easy to identify. It's the starting amount, in this case, 3,600. The B value is the hardest. A lot of people want to put 0.05. You got to be careful. It's always 100% plus the new 5%, which is 105%. Written as a decimal, move the decimal 2 spots to the left, you get 1.05. X in this case is 20. All right. So y equals 3,600 times 1.05 to the 20th power. You put that in the calculator and you will get $9,951.87. And that's the actual graph of what would happen. You can see it grows very quickly. Okay, that's the end of the growth lesson. The next lesson, we're going to talk about what happens when you decay.